Next up on our list is we're going to create equivalent rational expressions. So a theme here that I'm going to go with rational expressions is I'm going to talk a lot about rational numbers like fractions, and I'm going to try to equate what we're going to do or make parallels between rational expressions. So a lot of what we do with rational numbers, we're going to be doing with rational expressions. Multiply, add, subtract, and divide. Same strategies, much of them anyway. So at any moment with a fraction, we choose or we can multiply by 1, and it will not change the value. So for example, I can multiply 1/2 by 1 and it will remain as a half. So an expression is important if you manipulate it that you can't change the value. And we are often going to be multiplying it by 1. So before moving on to rational expressions, let's consider creating equivalent rational numbers. So 1/2 times 1 is equal to a half. Well, 1/2 is equal to a half. That's very unexciting. However, what I can do is I can do a very special type of 1 sometimes. Now, there is actually an infinite number of combinations I can do. But suppose I would like to create a denominator of 3. So if I want a denominator of 3, I'm just going to multiply the numerator and the denominator by 3. And this would create 3/6. Numerator times numerator, denominator times denominator. Now that is just one equivalent rational number to 1/2 is 3/6. And a lot of people develop this rule is, well, if you multiply the denominator by a certain quantity, you have to multiply the numerator by the certain quantity. And the reason for that is, and I've highlighted in pink, because the number 3/3 is actually a special type of 1. Let's move on to 4/5. Suppose I would like to create the denominator of 15. So I'm going to multiply. So I notice that my factor in the bottom is a 5, and I need to multiply 5 by something that will make it 15, and that is 3. But what I'm going to do is I'm going to multiply both top and bottom by 3. And that now 4/5 is expressed as 12/15. Now, 12/6 is kind of ridiculous. I don't know why. In my head, it's sort of hitting 2. I'm just going to maybe multiply something really weird. Never mind. I'm going to multiply it by 3. No, I already did 3/3. Pardon me. Perhaps I'm going to multiply it by 13. Now, I'm going to multiply both top and bottom by 13. Why? I don't know. But 6 times 13, I believe, is 78. 12 times 13, I believe, is 156. So 12/6, if I wanted to write it using using the denominator of 78, I would multiply both top and bottom by 13. And really, have I changed the value? No, because what I've highlighted in green is just 1. Now, making a connection to another unit in this course, I'm going to take 6/7. And let us rationalize the denominator. So perhaps I want to rationalize the denominator. How can I do that? Well, I multiply the denominator by √7. Why √7? Well, I picked √7 because √7 times √7 is equal to 7. Now, √6 times √7 is √42. So that's how we rationalize both top and bottom, or that's how we rationalize a denominator, but really, same strategy. It's a rational number, and we're just going to be multiplying by 1. Let's move on here. We're going to create rational expressions. And how are we going to do that? We are going to do that by multiplying both numerator and denominator by the same factor. I'm going to just choose random factors, if that's okay. So I have t minus 2 over t. That's what I start off with. And if I multiply both top and bottom by the same factor, really I'm just multiplying by 1. And if I multiply both top and bottom by that, I'm going to create the factor t minus 2t over t squared. So this is equivalent to this. Let's change it up just a little bit. So if I have, moving on over here, for x over x minus 2. Now, suppose, often is the case, I'm just going to put brackets around. A lot of people work better with brackets. So if you work better with brackets and you can see things more easily, please put brackets. So I have 4x divided by x minus 2. Now, I could multiply both top and bottom by anything, like 3 over 3, 2 over 2, x over x. But here, and it's really quite arbitrary, it doesn't really matter. I'm just going to maybe say, why don't I multiply both top and bottom by the conjugates? Now, I'm going to introduce another restriction, right? So this cannot be equal to 0, which is reflected in my restriction, x can't be equal to 2. However, I just introduced this as a denominator, so I'm going to say x can also not equal to negative 2. So it also changes your restrictions. However, when we multiply it, there we have it. So the two expressions that are in yellow are considered equivalent. All we have to do is multiply both top and bottom by the same factor, which is actually multiplying by 1. All right. So I'm going to demonstrate that the following are rational expressions. So I'm just going to take a look here and here. Are these rational expressions? Well, I'm going to take a look. I'm going to call one the left-hand side. I'm going to call one the right-hand side, if that's okay with you. What we notice is that the left-hand side has a factor of x minus 2. Whereas the right-hand side has a factor of x minus 2 and x plus 2. So essentially what I'm going to be doing is I'm going to be multiplying by, or I'm going to be multiplying by 1. And what do I want? I want a factor of x plus 2 in both the numerator and the denominator. And wouldn't you know it, when you multiply the numerator, it creates the factor of x plus 2, and the denominator has factor x minus 2, x plus 2. All right, the bell is going. Give me one moment here. I'll try to make this quick. Now, here. Oh boy, that's nasty. So I have the left-hand side. I'm going to write left-hand side, and I'm going to have the right-hand side. Well, guess what? We are going to have to factor. So I'm going to factor the top. Why? I don't know why. I'm just going to do this. I'm going to factor the bottom. So x squared plus 5x plus 6. That's the product sum rule. Two numbers that multiply to 6 but add to 5. There we have it. That's what the right-hand side looks like. But the left-hand side is x and x plus 3. Now, if you notice, on the left-hand side, I have a factor of x plus 3. Same on the right-hand side. However, on the right-hand side, I'm missing the factor of x plus 2. So I'm just going to simply multiply both top and bottom by x plus 2. So this is the left-hand side and right-hand, so that's the left-hand side. And what we see is that these two are rational expressions. However, I have the new restrictions that x cannot be equal to negative 3 or negative 2 from the factors respectively. I may choose to write it as x plus 2 altogether, x plus 3 over x plus 2. The left-hand side is equal to the right-hand side, so we have equivalent expressions.